Mercury should already be a dead planet. Scientists thought the humble hunk of rock that's only slightly girthier than Earth's moon would have been battered to barrenness by the sun's intense solar radiation. It's a hostile world. The day and night sides of the planet see a temperature difference of nearly 600 degrees Celsius. But Mercury has proved to be a world of contradictions, a dynamic planet that hides more surprises than scientists initially gave it credit for. A thin atmosphere, a magnetic field, and a stash of volatile compounds still persist on Mercury, features that scientists usually associate with planets that are larger and farther away from the Sun. While new observations from the last few decades have given scientists good cause to revise their opinion of Mercury.
Mercury is basically a big ball of metal surrounded like a tiny bit of rock. And the major question is, why? Why is it like this when the rest of the planets aren't?
Its secrets remain. But now, by using powerful telescopes, scientists have stumbled upon these secrets. But what they found is so weird. There is something moving that they never saw anywhere else. Such a stunning revelation could even lead to crucial missions to reveal a terrifying truth about our universe. Join us as we shed light on the dark shadow that Mercury has kept under wraps. Named for the fleet-footed Roman messenger god, Mercury is the closest planet to the Sun, zipping around our parent star at an average of 36 million miles away. However, Mercury's orbit is not a perfect circle. The planet can pass as close as 29 million miles and as far away as 43 million miles. Living up to its name, Mercury is the fastest planet in the solar system, speeding along at about 29 miles per second and completing each orbit around the Sun in just 88 Earth days. Mercury is also the smallest planet in the solar system, measuring just 3,032 miles wide at its equator. That makes it only slightly larger than Earth's moon. Because Mercury is so small and so close to the Sun, it is the most elusive of the 5 planets that are visible to the naked eye. You can only catch Mercury at dawn and dusk, and it usually does not rise far above the horizon. But that's not the only time the tiny planet makes an appearance. Because of its position in the solar system, Mercury passes between Earth and the Sun 13 times each century in an event known as a transit. During a transit of Mercury, observers on Earth can see the planet in silhouette as it seems to sweep across the Sun's disk. Since ancient times, people observing the heavens have noticed that the naked eye planets sometimes appear to move backward, briefly shifting from their usual eastward motion to a westward path across the sky. This retrograde motion is an illusion created when one planet moves faster in its orbit than another, so that it catches up to and passes the slower world. For observers on Earth, Mercury is in retrograde about 3 to 4 times a year. If you could watch the skies from the surface of Mercury, you would sometimes catch the rare sight of the Sun in retrograde. As Mercury makes its closest approach to our smoldering star, its orbital speed exceeds its rate of rotation on its axis. That means someone standing on Mercury would see the Sun start to rise, then briefly set, then rise again, all within the same day. Like the other planets in the solar system, Mercury was born about 4.5 billion years ago, condensing from the swirling ring of dust and gas left over from the Sun's formation. The small planet cooled very quickly, contracting enough within the first billion or so years to prevent magma from escaping through the outer crust and ending geologic activity such as volcanism on the surface. And while Mercury may be small, it's hefty. Although its diameter is barely larger than the Moon's, Mercury is over 4 times as massive as Earth's natural satellite. In fact, Mercury is the second densest planet in our solar system, after Earth. The planet's extreme density comes from the fact that it has a large iron core that makes up about 60% of the planet's volume. In contrast, Earth's core by volume is only about 15%. The abnormal internal structure has spawned several theories on Mercury's birth. Scientists think that perhaps early Mercury's outer layer was boiled away by the sun or scattered by solar winds. Or perhaps the young planet could have been struck by a large impactor that stripped away most of the softer outer layer, leaving behind its sturdier heart. Since part of the mantle and crust are still present today, this suggests that the collision may not have been a head-on smack, but a glancing brush that preserved some of Mercury's original layers. The first mission to Mercury, Mariner 10, was launched in 1973 and found that Mercury still sustains a magnetic field. The discovery came as a shock to the scientific community, who had assumed that such a small planet would have rapidly cooled, and its insides would have congealed, thereby losing any means of magnetism at the global scale. The presence of a magnetosphere implies that part of Mercury's core is still churning. Mercury's magnetic field is about 100 times weaker than Earth's on their respective planetary surfaces. The sluggish dynamo means that the planet is at the tail end of its developmental stage, on its way to becoming a dead planet like Mars. In the 2010s, the second Mercury mission, Messenger, documented that the planet's magnetic field is off-kilter. The magnetic South Pole doesn't sit on the geographic South Pole. Instead, it is buried almost at the center of the planet. The magnetic field offers a glimpse of the planet's interior and a snapshot of its history, hinting at how far the whirling insides have decelerated over billions of years. Due to its proximity to our star, Mercury is hot. If we're being quantitative, it's actually extremely hot. As the closest planet to the Sun, it completes an orbit in just 88 Earth days, achieving a maximum temperature during the day of a whopping 427 °C at its hottest equatorial locations. Mercury rotates very slowly, so its night side spends a consecutively long time in the dark, shielded from the sun. During those times, it gets down to just minus 173 degrees. That low temperature is incredibly cold, and far colder than any known naturally occurring temperatures here on Earth. But despite being the closest planet to the Sun, Mercury is not the hottest planet in the solar system. Venus is about twice as far from the Sun on average as Mercury is, taking about 225 Earth days to orbit the Sun. It also rotates even slower than Mercury, spending more than 100 consecutive Earth days at a time bathed in sunlight, and then an equal amount of time in darkness. And yet, when you measure the temperature of Venus, there's a surprise. Venus is the same temperature at all times, day or night, at an average of 462 °C, making it even hotter than Mercury. This strange occurrence did more than just puzzle astronomers when they first discovered it. It mortified them. Venus wasn't large enough to generate its own heat, and yet it was hotter at Venusian midnight than at Mercurian high noon. Why is that? Well, that is because of the main difference between the two worlds. Venus has a very substantial one that's some 190 times as thick as Earth's is, but Mercury, instead of a substantial atmosphere, has such a thin atmosphere that it doesn't really qualify as an atmosphere. Instead, scientists call this wispy layer of gas an exosphere, where the gas is so rarefied that it hardly registers a pressure reading. Mercury takes a constant beating from the Sun, so its exosphere has to regenerate itself from the surface. Since the 1980s, astronomers have detected in Mercury's exosphere atomic sodium, potassium, and calcium, metals with strong emission signals that can be observed all the way from Earth with telescopes. These metallic elements are not usually thought of as gases, but they find their way into Mercury's skies by dint of solar particles and meteorites striking the planet's surface. Solar winds gouge the resulting exosphere, and the interactions between the gases and sun-flung particles fashion a 15-million-mile-long glowing tail behind Mercury. This tail lengthens and shrinks seasonally, depending on Mercury's proximity to the Sun. If you were standing on Mercury and looking up at the right time of the year, Mercury's long tail would appear in the sky as a faint orange glow. as if the heavens were illuminated by sodium streetlights. A planet perched right at the sun's maw shouldn't harbor any water, let alone ice, or so researchers thought. But in the 1990s, scientists at Goldstone in California and the Arecibo radio telescope in Puerto Rico directed a stream of radar signals toward Mercury. The teams were astonished to observe two brightly reflective spots at the poles, likely icy deposits. In 2012, MESSENGER confirmed that the ice at Mercury's North Pole was frozen water. Laser measurements on board identified carbon-rich material on the surface that insulates an ice pack underneath. Mercury has managed to cling on to its water because it has pockets in permanent shadow. Relative to its orbit around the Sun, the planet spins perfectly upright, like a soldier at attention facing a commanding officer. That means the impact craters near the poles have insides that never see any daylight. Temperatures within these divots dip below -173 degrees Celsius, close to the temperature where nitrogen gas liquefies. It's cold enough that ice can be stable over geological timeframes. And as on most other rocky planets, the water on Mercury probably came from asteroids that crash-landed onto the surface. This water hides in Mercury's craters, untampered with since primordial times. On other terrestrial planets in the solar system, geological processes such as weather cycling have scattered the externally delivered water all around the globe. If scientists want to sample ancient ice in its pristine form in the solar system, the best source is probably Mercury's poles. Mercury defied expectations again when MESSENGER detected volatiles on the sun-scorched world. Volatiles are chemicals that can jump between solid and gas phases in a short temperature change. Mercury already proved it sheltered water, a volatile, but MESSENGER found others such as sulfur, potassium, and chlorine that easily vaporize at moderately high temperatures. These volatiles are distributed all across the surface of the planet. For its size, Mercury contains as much volatile content as other terrestrial planets in the solar system that are farther from the Sun and hence much colder. Where the volatiles come from and how Mercury has retained them are still matters of scientific debate. Some researchers think that the volatiles came from underground relatively recently, while others think the chemicals have persisted on the surface since an embryonic Mercury condensed from its protoplanetary disk. The volatiles on Mercury raise questions. For example, if planets that edge up against their stars have volatiles, especially water, could these locales also be habitable? Well, it's possible that Mercury once held the ingredients for life. Indeed, Mercury has irregular depressions in the ground, called hollows. Mariner 10 first glimpsed them in 1975. Then, MESSENGER photographed these shallow tracts at fine resolution. The depressions span from a few dozen feet to over a mile across, and they may be as deep as 120 feet. They look like the soft, airy insides of a sourdough loaf cut open. The hollows may be the doing of volatiles, scientists theorize. Since the atmosphereless Mercury has no rain or wind to carve the land, surface features like hollows can only be formed from other processes, such as the ground leaking volatiles into space. Hollows are relatively young formations, about 100,000 years old on average, compared with some 4 billion-year-old impact craters on Mercury. Scientists think hollows are still forming today, and hollows are unique to Mercury. No other celestial body in the solar system seems to present similar pockmarks. In recent years, scientists have identified other structural formations on Mercury, chaotic terrains, jumbled ridges that look like a failed game of Jenga, cut up vast swaths of the land. Some researchers think the chaotic terrains are the result of the ground wafting volatiles until it loses structural integrity and collapses. Other scientists think that chaotic terrains form after ripples from an asteroid impact encircle the planet and meet on the opposite side of the globe. In addition, Mercury's topography also provides clues that volcanoes once spewed lava on the planet. Mariner 10, first glimpsed and then Messenger later confirmed that glossy plains spread across Mercury's surface. Each plane suggests pooled lava smoothed over older craters and ridges. Researchers think that magmatic volcanism halted on Mercury anywhere between 1 billion to 3.5 billion years ago, due to planetary cooling and contraction that plugged up the magma's escape routes. Mercury has also shown signs of another kind of volcanism, explosions. If streaming lava is like a runny nose, then explosions are the volcanic equivalent of a sneeze. Irregular pits several miles across and more than 2 miles deep hint at ancient pyroclastic volcanoes that self-destructed. Scattered around these pits are deposits that researchers think are ejecta from the explosion. These types of volcanic bursts are probably caused by volatiles underground. When these buried chemicals rise to the surface, they expand in volume. Eventually, the pressure buildup of gases causes the volcano to pop, like an overfilled balloon. But volatiles, a chemical category that includes water, are essential for sparking and supporting life as we know it here on Earth. So, their potential presence on Mercury is an intriguing development. Astronomers now speculate that beneath the scorching surface of Mercury, the closest dwarf planet to the Sun, there could be signs of life. But how could volatiles, which are essential to life here on Earth, survive on a planet whose daytime temperatures soar to 430 degrees Celsius and drop to minus 180 degrees Celsius at night? Alexis P. Rodriguez, a researcher at the Planetary Science Institute in Arizona, explained that while the planet's surface swings wildly between temperature extremes, just below the surface, temperatures are milder. In the words of Rodriguez, it's likely that there was some sort of water that formed in part of Mercury's crust, but the team cannot yet tell exactly what volatiles were present when the planet's surface broke apart. While the mystery remains, a completely unexpected discovery made by NASA's Messenger spacecraft revealed that a 10-mile-thick diamond mantle may lie beneath the crust of Mercury. While instances of such valuable encrustation might sound tantalizing, turning these precious stones into fashionable jewelry remains an impossibility due to their inaccessible location deep within the planet. However, these gems could hold the key to unraveling some of the big unanswered questions circling around Mercury composition and its rather curious magnetic field. These diamonds may facilitate heat transfer between the core and mantle, thereby creating temperature differences and causing liquid iron to circulate, a process that would kickstart the creation of a magnetic field. The discovery of a potential diamond layer within Mercury opens new avenues for planetary research and composition studies, not only of Mercury, but also of other celestial bodies. Understanding the unique geological characteristics of Mercury could provide deeper insight into the formation and evolution of the solar system. The new discovery also prompts a reconsideration of the processes involved in planetary formation. Diamonds are typically associated with high-pressure environments, suggesting that similar conditions may exist in other distant rocky exoplanets and moons within our solar system. Studying extreme planetary conditions can reveal not only the composition of these bodies, but also the historical processes that formed them, leading to a more comprehensive understanding of geology across the cosmos. The potential discovery casts a new light on the evolution of carbon-rich exoplanets. The process that led to the formation of a diamond layer on Mercury could also be at play on other planets, possibly leaving similar traces. The arrival of the Bepi-Colombo spacecraft, a joint mission of the European Space Agency and the Japan Aerospace Exploration Agency, in 2025 will provide better opportunities to delve deeper into this intriguing discovery. Bepi-Colombo was launched in 2018 on a complex trajectory to the solar system's innermost planet. The ESA reports that the spacecraft's thrusters have lost some power. Bepi-Colombo's mission is to complete a comprehensive investigation of Mercury's magnetosphere, magnetic field, and internal and external structure. But traveling around in the inner solar system is complicated, and the Bepi-Colombo spacecraft will use more energy getting to Mercury than it takes to get to Pluto. The spacecraft will perform 9 planetary flybys before reaching its destination at the end of 2025. Bepi-Colombo has already performed 1 gravity assist at Earth, 2 at Venus, and 5 at Mercury. It'll perform 1 more at Mercury in January 2025. The Mercury Transfer Module, or MTM, is the part of the spacecraft that delivers a pair of orbiters to Mercury. On April 26th, as the spacecraft was about to execute its next maneuver, the MTM didn't deliver enough electrical power to its thrusters. A team working on it restored the thrust back to 90% on May 7th. But the MTM still isn't deliver enough electricity to get back to 100% thrust. Despite the power problems, the spacecraft is on track to complete its final Mercury flyby. A team is working to maintain the current power level and to understand how the diminished thrust will affect future maneuvers. They're also working on restoring full power to the thrusters. To facilitate this, the mission's flight control team at the European Space Operations Center in Darmstadt, Germany, has arranged additional ground station passes. Bepi-Colombo employs a solar electric propulsion system. 2 15-meter-long solar cells gather energy and deliver it to 4 ion thrusters that use xenon propellant. The thrusters are mounted on gimbals, making them aimable. Bepi-Colombo consists of 3 separate spacecraft. The Mercury Transfer Module is kind of like a tugboat, delivering 2 separate orbiters to Mercury. One of the orbiters is the Mercury Planetary Orbiter, and it carries 11 scientific instruments, including cameras, several spectrometers, a magnetometer, and others. The other one is the Mercury Magnetospheric Orbiter, largely built by JAXA. It carries 5 groups of instruments, including one group that will study the plasma and neutral particles from the planet, its magnetosphere, and the solar wind. While waiting for the first data obtained by Bepi-Colombo, scientists also put their hope in another tool, the James Webb Space Telescope. The Supreme Space Telescope comes with significant advantages over any previous mission. First and foremost is its size. James Webb features a 21.7-foot mirror composed of 18 gold-plated hexagonal segments. This colossus gathers more than 6 times as much light as the Hubble Space Telescope's 7.8-foot mirror, so it can record light from objects 6 times faster than its predecessor. But Webb's sensitivity to infrared light is the real game changer. The Space Telescope can view wavelengths from the red end of the visible spectrum to the mid-infrared. Hubble's optics are optimized to record radiation from the ultraviolet to the near-infrared, with the majority of its sensitivity centered on visible light. Perhaps surprisingly, in its intended infrared domain, James Webb generally won't resolve finer details than Hubble achieves in optical light. Although resolution increases with mirror size, it also diminishes with wavelength. Observing in the infrared allows astronomers to see galaxies that existed less than 1 billion years after the Big Bang. These distant objects emit ultraviolet and visible light, but the expansion of the universe shifts this radiation to longer infrared wavelengths. Peering into the infrared is the only way to observe these young galaxies from Earth's vicinity. The same holds true for newly forming stars. The dust that envelops infant suns scatters visible light, hiding what lies within from our eyes, but it lets infrared radiation largely pass through. Despite its focus on distant galaxies and star formation, James Webb is an all-purpose observatory. Its powerful infrared eye sees details in solar system objects beyond the reach of conventional telescopes. Early observations include studying cloud belts on the gas and ice giant planets, tracking cloud formations on Saturn's largest moon, Titan, exploring Pluto's climate, and probing many of the smaller asteroids and trans-Neptunian objects that populate the outer solar system. The telescope even observed the asteroid moonlet Dimorphos in September, when NASA's double asteroid redirection test slammed into it. The impact slightly changed the object's orbit around its parent body, Didymos, helping the space agency assess its ability to alter the course of potentially hazardous asteroids that could cross Earth's path. Thus, it's not far-fetched to think of the Space Observatory can take a closer look at Mercury, unlocking the subterranean secrets of the closest planet to the Sun. In the latest observation, using James Webb, astronomers discovered that Ariel, a moon of Uranus, could be hiding in a buried liquid water ocean. The discovery could supply an answer to a mystery surrounding this Uranian moon that has perplexed scientists. The fact Ariel's surface is covered with a significant amount of carbon dioxide ice. This is puzzling because at the distance, Uranus and its moons exist from the Sun, 20 times further out from the Sun than Earth. Carbon dioxide turns to gas and is lost to space. This means some process must refresh the carbon dioxide at the surface of Ariel. Previous theories have suggested this happens as a result of interactions between Ariel's surface and charged particles trapped in Uranus's magnetosphere that provide ionizing radiation, breaking down molecules and leaving carbon dioxide, a process called radiolysis. However, new evidence from the Webb telescope suggests the source of this carbon dioxide could come not from outside Ariel, but from its interior, possibly from a buried subsurface ocean. Because chemical elements and molecules absorb and emit light at characteristic wavelengths, they leave individual fingerprints on spectra. The team behind this discovery used James Webb to gather spectra of light from Ariel, which helped them paint a picture of the chemical makeup of the Uranian moon. Comparing this to simulated spectra from a chemical mix in the lab here on Earth revealed to the team that Ariel has some of the most carbon dioxide-rich deposits in the solar system. Not only did this add an extra 0.4 inches of thickness to the ice on the side of the tidally locked Ariel that permanently faces away from Uranus, but it also revealed clear deposits of carbon monoxide for the first time. As team leader Richard Cartwright from the Johns Hopkins Applied Physics Laboratory, or APL, said in a statement, "It just shouldn't be there. You've got to get down to 30 kelvins, minus 405 degrees Fahrenheit, before carbon monoxide's stable. The carbon monoxide would have to be actively replenished, no question." That's because Ariel's surface temperature is, on average, around 18 degrees Celsius warmer than this key temperature. Cartwright acknowledges that radiolysis could account for some of this replenishment. However, observations from Voyager 2's 1986 flyby of Uranus and its moons and other recent findings have suggested that the interactions behind radiolysis could be limited because Uranus's magnetic field axis and the orbital plane of its moons are offset from each other by about 58 degrees. That means that the majority of the carbon-oxygen compounds seen on Ariel's surface could be created by chemical processes in a liquid water ocean trapped under ice on Ariel. Once created in the seep water ocean of Ariel, these carbon oxides could then escape through cracks in the icy shell of the Uranian moon, or could even be explosively ejected by powerful eruptive plumes. Scientists have suspected for some time that the cracked and scarred surface of Ariel may indicate the presence of active cryovolcanoes, volcanoes that erupt plumes of icy slush rather than lava. These plumes could be so powerful that they launch material into Uranus's magnetic field. The majority of the cracks and grooves seen on the surface of Ariel are located on the side of the moon that faces away from Uranus. If carbon dioxide and carbon monoxide are leaking from these features to the surface of the Uranian moon, this could explain why these compounds are found in greater abundance on this trailing side of the icy body. In addition, James Webb also picked up more chemical evidence of a subsurface liquid water ocean. Spectral analysis hinted at the presence of carbonate minerals, salts created when rock meets and interacts with liquid water. As Cartwright explained, if our interpretation of that carbonate feature is correct, then that is a pretty big result because it means it had to form in the interior. That's something we absolutely need to confirm, either through future observations, modeling, or some combination of techniques. Uranus and its moons haven't been visited by a spacecraft since Voyager 2 almost 4 decades ago, and this wasn't even the spacecraft's primary mission. In 2023, the Planetary Science and Astrobiology Decadal Survey emphasized the need to prioritize a dedicated mission to the Uranian system. Cartwright believes such a mission would present an opportunity to collect valuable information about Uranus and Neptune, the solar system's other ice giant. Such a mission could also deliver vital data about the other potentially ocean-bearing moons of these systems. This information could then be applied to extrasolar planets or exoplanets beyond the solar system. As team member and NASA Applied Physics Laboratory scientist Ian Cohen said, all these new insights underscore how compelling the Uranian system is, whether it's to unlock the keys to how the solar system formed, better understand the planet's complex magnetosphere, or determine whether these moons are potential ocean worlds. Many of us in the planetary science community are really looking forward to a future mission to explore Uranus. In another remarkable study made by James Webb, astronomers have investigated a new super-Jupiter planet that is one of the coldest worlds ever seen outside the solar system. The exoplanet is located in the triple star system Epsilon Indi, which sits around 12 light-years away. The planet is designated Eps Ind Ab and has a mass around 6 times that of Jupiter. It orbits its red dwarf parent star at a distance similar to that between Neptune and the Sun. This gives the world a surface temperature of around 0 degrees Celsius and means one orbit of the planet takes around 200 Earth years. The Webb telescope was able to image the exoplanet using the sensitive infrared capabilities of the mid-infrared instrument. The investigation of Eps Ind Ab could help astronomers better understand the evolution of gas giant planets and their systems. This is the first time that the powerful space telescope has been able to image an exoplanet that wasn't previously imaged from the ground. Eps Ind Ab is also the coldest exoplanet James Webb has been able to study thus far. That's why scientists were excited when we realized we had imaged this new planet. To their surprise, the bright spot that appeared in our MIRI images did not match the position we were expecting for the planet. They added that previous studies had correctly identified a planet in this system, but had underestimated the super-Jupiter gas giant's mass and orbital separation. The team was able to correct this with the help of James Webb. The crew determined the planet has a highly elliptical, or flattened, orbit that, at its closest, brings it to a distance about 20 times the distance between Earth and the Sun. At the furthest point in its orbit, Eps Ind Ab is 50 times further away from its parent star than the average distance between Earth and the Sun. The world's parent star, a red dwarf named Eps Ind A, has 2 stellar companions. Both are brown dwarfs, or failed stars, named as such because they're objects that form like stars but can't gather enough mass to trigger nuclear fusion processes in their core that define what a main sequence star is. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.
Mercury is basically a big ball of metal surrounded like a tiny bit of rock. And the major question is, why? Why is it like this when the rest of the planets aren't?